All right. Last time I mentioned, among other things, the following result. The theorem which has two parts. So if we have L linking the three sphere, then we can decompose it uniquely as a connected sum of the global part and the local part. And this was Rolson's theorem. But also, if L is a string link, then again we have the same decomposition. Maybe gamma. But the interesting thing is that if you take the closure of the string link, then you will not get the same decomposition. The local part of the closure may be different from the local part of the string link. This is something that I didn't know the last time, but here is an example. Yes, so this goes here, this goes here. Okay, my example must be a string link. So I can draw like this. So I think that this string link has no local nodes. Well, if you take the closure, then definitely you will get a local node.
Ну, имеется в виду белый, можете объяснить? Я не знаю.
Okay, let me draw the closure. So in this closure, you can, for example,
получится две струны.
yes. So this part can be a shrunk, and then you can pull here, and then you get just the trefoil. So the closure has a local node, this trefoil. But if you don't take the closure, then I don't think that there is any local node. I didn't really have time to prove this, but the idea of proof is follows, which has to be checked yet. We can take a different closure. can take the closure. Well, this can be the same. And these two can be connected like this. So what you get is a sort of a Whitehead link where, let me try to redraw it.
То есть можно желтый с красным соединить, белый с красным соединить?
Well, I can do whatever I want. It is possible to consider whatever I want. The question is, what can I prove by this? but let me try to redraw. So it's similar to the Whitehead link, but here we put the trefoil somehow. Just like this. So I think this is what you get when you close it up like this. Is it right? and this link, I think it should be possible to prove that it has no local nodes. Maybe just by the Conway polynomial. Because if there is a local node, then the Conway polynomial will be the product of the Conway polynomial of this local node and the Conway polynomial of what remains. So if we can show that that the Conway polynomial is not divisible by any one variable. Yeah, okay, so I think it has to be the two variable Conway polynomial, but anyway, yes. So if we show that if it is not divisible by any one variable polynomial, then this will be proved. And it's probably true. It has to be checked, but it's probably true. Because if you make the intersection here, then in there is a Conway skein relation, it gives you two circles. So you get quite a simple picture, trefoil with two such circles. It's a three-component link, and I think it should be detectable.
Я не понял. Вы взяли, пересоединили каким-то образом, и что вы сейчас показываете?
Yes, okay. So so I didn't prove that this link doesn't have a local node, but suppose that this is proved.
Да.
Then the string link also doesn't have a local node. Because what is a local node? A local node means that there is a ball which intersects the link in an arc. And this arc is knotted inside the ball. But if there is such a ball in the cube which contains this string link, then in particular there is such a ball when we take any kind of closure. So
Но вы же только что замкнули и сказали, что там нет, что есть локальный узел.
I think there is no local node here in this
Ну,
picture. When I take the standard closure, there is a local node. But when I take the strange closure, there is no local node.
Ну, хорошо.
And this means that in the original string link there is no local node. Because if the original string link has a local node, then every closure must have a local node.
Ну ладно.
А вот если там есть локальный узел, то он есть на какой-то конкретной компоненте. Вот, допустим, на правой картинке, вот это доказать. Вот он на какой-то конкретной компоненте. Ну, тогда получается эта компонента сама в себе. То есть вот здесь каждая компонента, ну, одна компонента тривиальный узел, другая трилистник, то есть простой узел. Значит, единственный способ там стянуть какой-то локальный узел, это превратить трилистник в тривиальный узел.
Okay, you're right. Yes, it can be proved maybe in a different way also. That yes, by your argument, if there is a local node, then it must be the trefoil. Yes, this can simplify the proof, but still there is something to be proved.
А коэффициент сцепления у них Ну, любой...
Well, it's almost obvious, I agree. But
Значит, в string link нету local node, потому что можно так замкнуть, что получится link без local node. Ну, и есть такое замыкание, что есть local node.
yes, the standard closure has a local node. The previous one, which was like this.
Ну, то есть, значит, определение локального узла для string link является более общим по сравнению, ну, надо все замыкания перебрать и посмотреть, есть ли там local node.
Maybe. But the two decompositions are really different. And so I think that the second part, if I call this part A, and this part B, I think that part B does not follow from part A, and it cannot be deduced from part A. But I have a proof of part B, a different proof. So it can be proved, both parts can be,
Теорема в чем заключается?
that there is a unique decomposition, both for links and for string links. But these two decompositions are different because of this example. So, I don't know if we want to discuss the proof of this theorem. Maybe if we have time, if you want, then we can discuss it after the break. I can do it. So this proof is similar to the proof of Hashizumi's theorem about unique decomposition of a link into prime links. And actually, this Hashizumi's theorem is not so difficult. I told you last time that it's a difficult theorem, but no, it is quite easy. My proof is just 2 pages. Hashizumi has a quite long proof, 16 pages, but half of them is figures. And I have just 2 pages and no figures. So,
Упростили доказательство называется.
yes. I got rid of the figures, and also, but the reason why he has so many figures is because he considers many cases. And I don't consider many cases, just 2 cases for all proof. Okay, so this example is related to the mistake which you found last time in my proof. And this is why I started from this example. So there is the following problem. If 2 links L and L prime are n quasi-isotopic, are they closures of n quasi-isotopic string links? So we want 2 string links which are n quasi-isotopic, and their closures are our given links. Okay? Yes, and we can put a different number here. It can be R. So is it true that for any R there exists an n such that so I don't know the answer to this problem, either with the same n or with n and r. But last time I told you that I can prove it. It was a mistake, sorry. So why I think that this problem is difficult? Because in this example you can take some self-intersection, for example here. and then the trefoil will be made into the trivial knot by this self-intersection. So then, when you take the usual closure, there will be no local knot. So there are two pictures, before the intersection and after the intersection. Maybe I should draw the standard closure. So there is an original picture, and then the same picture, but after the self-intersection.
Тривиальный будет после.
Yes, it will be trivial. Something like this. Let me now show the other part. So, when I do such an intersection, and yes, if I take the closure here, this will be an n quasi-isotopy for each n. Because here, this knot is local. I can, after I take the closure, this knot is local. I can just shrink this part and take it out, and this knot is local, so there is a ball which contains this knot, but this ball doesn't contain this stuff. So this ball is, it looks like this.
Если он тривиальный, понятно, что есть.
Yes, it's difficult to draw it, but there exists such a ball which contains this trefoil and doesn't contain the other components. And when I do this self-intersection, it is inside the ball. And in the definition of n quasi-isotopy or strong n quasi-isotopy, there is a sequence of balls. But I can just take the same ball every time, 100 times or 200 times. And this ball works because it intersects the knot in 2 points. And so there is no reason to make it larger and larger. The ball will, it's necessary to make it larger if it intersects additional parts of the same component. Then I have to make it larger. But if it intersects a knot in an arc, then the same ball works for every index. So it's an n quasi-isotopy for each n after I take the closure. But before I take the closure, of course it is not, I think it is not even one quasi-isotopy. Probably. It doesn't look like a one quasi-isotopy. So this is the problem which we discussed last time, that we have this ball in the 3 sphere, and we cannot squeeze this ball into the cube. Well, last time instead of the ball, I was speaking about a 2-dimensional disk which intersects all components, in each component in a point. This was mentioned last time. So to get from a link in S3 a string link, you just need to draw such a disk, and then it gives you automatically a string link. Because if you take a regular neighborhood of this disk, it will be a ball, and you can just subtract this ball, and what remains is homeomorphic to the cube. But the problem now is that we have a ball, we have another ball, this brown ball, which intersects this thing, and I cannot remove these intersections because I cannot push this ball inside of the cube. Okay?
Сергей Александрович, а разве уже не... Вот если считать, что вот справа нарисованное зацепление не имеет локальных узлов, то разве не доказано, что вот то, что вы проделали с левым, ну вот то, что проделали со струнным зацеплением, не является один квазиизотопией? Потому что если это один квазиизотопий, то можно вписать в шар дугу вот пересечения до себя. А ну, получается, снаружи этого шара узел будет тривиальный, и если этот рейс не включается в шар, то получается внутри его как раз и можно стянуть. И получится...
Well, if we assume that there are no local nodes here, then it proves that, or it can be deduced, at least using this theorem, that there is no PL isotopia which kills this node. But about one quasi-isotopia, it's a different question, or even strong one quasi-isotopia, because in the definition of one quasi-isotopia, this ball doesn't have to intersect the node in just 2 points. It can intersect it in additional points. So this is a more difficult situation. I think about strong one quasi-isotopia, you cannot prove it immediately in such a way. So why do we want to do this? Why do we want to get rid of such intersections? Because if we are given an n quasi-isotopia, it can have several self-intersections of a component. And of course, yes, so maybe this should be called a lemma. So if we have just one intersection in n quasi-isotopia, then this problem has a positive solution, and it's easy. Because, so what is n quasi-isotopia? N quasi-isotopia is when you have a self-intersection. Well, this is one, n quasi-isotopia was one self-intersection, so this is n quasi-embedding. So we have some complicated component. And then we have some balls which contains this, maybe it contains this, and then because of this it has to contain more, the next ball, and then the next ball contains still more. Somehow there is also the second component somewhere. And certainly so we have a sequence of balls B. So this intersection point X lies in B1, then B1 lies in B2, and so on. B. And this is a singular link in the 3 sphere. We want to represent it as a closure of a string link, but with the same sequence of balls. But there is no problem to do it. We can find such a disk here, away from these balls. We can draw it like this. So And this disk is disjoint from this brown ball, and if we take its small regular neighborhood, this will be a ball which is disjoint from this all these brown balls. And then the complement to this regular neighborhood will be homeomorphic to a cube which contains a sequence of such brown balls. So in the case of one self-intersection, this problem has a positive solution and it is trivial. Okay? But if we have more than one self-intersection point, so we have a homotopy. We have this L, which is L0. Then there is a self-intersection, and we get L1. A self-intersection, we get L2. A self-intersection, we get L3, and this is L prime, for example. So for these links, I have to, if I represent them as closures of string links, I have to do it in a ways that agrees for different links. Like here I take the same green disk before and after this intersection. So I also want to do something like this. But if I do this green disk for this first intersection, and then I have the second intersection which is somewhere else, but then this green disk doesn't work for a second intersection. I need to draw a different green disk somewhere here. But this is a problem because I want to find string links here, lambda 0, lambda 1, and n quasi-isotopic is here. But I want L0 to be the closure of lambda 0, L1 to be the closure of lambda 1, and so on. And it is a problem because then these green disks must be the same, but I cannot make them the same. And to make them so the idea which I tried to use last time is that we take one green disk and try to push it through all these crossing changes. But this means that we have, for the next sequence of balls, we have to squeeze them inside the cube, and we cannot do this. So there is some problem. I don't know how to solve this problem if we have more than one intersection point. But the lemma says that we can solve it for one self-intersection point. Maybe I write it here, just like this. Lemma. This one intersection point then they are closures of n quasi-isotopic string links.
Александрович, можно немножко поменять расписание? Вы что-нибудь без доказательств расскажите до обеда, а потом с Мишей разберетесь, я послушаю. Я сегодня немножко пораньше хочу пойти, ладно? Или вы сейчас уже не можете?
So we proved this lemma, it is a trivial lemma. If we have one quasi-isotopic with one intersection point, then we can do it by string links. And using this lemma, I can prove again the main theorem. The main theorem is that topological isotopy implies PL isotopy, assuming that finite type invariants separate links. So I can do this now, modulo theorem 3. And theorem 3 then I have to prove. Okay?
Ну да, нет, ну я понял. Но можно повторить, да, доказательства. А лемму вы вроде объяснили, или хотите еще формально доказать?
Yes, I think the lemma is proved. Yes?
Ну, наверное, не знаю.
Well, if we have an n-quasi-isotopy with one intersection point, we have such a sequence of balls, but the maximal ball Vn is still doesn't contain all the component. There must be an arc outside of it, and also it doesn't intersect the other components. So we can find such a green disk outside this maximal ball.
Почему не это самое, это по определению зеленый диск не пересекает? Если квазиизотопия.
Yes. So the definition of n-quasi-isotopy is that there are such balls and also arcs. The last arc lives in the domain, the M circles. But these are arcs, and also we are required that this map F n quasi-embedding it satisfies the following: F inverse of each Bi lies in Ji. And also I think Bi union with F of Gi lies in Bi plus 1. But this says that the last ball, the preimage of the last ball lies in the arc. So it doesn't contain this entire component, and it doesn't intersect other components. So we have the following implications. L and L prime topological isotopic and they are okay for each n they are n quasi-isotopic this was theorem 1. Then, by this lemma, for all n, L and L prime are n quasi-isotopic via string links. So what does this mean? This means that we have such a picture, elementary n quasi-isotopies here with one self-intersection point. But here we have a different picture. We have one closure here and two closures here. Maybe lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. So here we have an n quasi-isotopy with one self-intersection point. Here is just ambient isotopy. Then again we have, no, sorry. It's so these are string links, and these are links. And we start from here. No.
Мне кажется, там круг замыкался, если...
Sorry. Sorry, it was right. Yes, it was right. There is just no equality here. There is a closure. Yes. So the picture is like this. Okay.
Ну, время, ладно, одна точка. Значит, вы сейчас объясняете определение.
I'm explaining the definition of n quasi-isotopic string links.
Не было определения. Вы объясняете неформально, да? Значит, там есть одна точка между L0 и L1. И что это крестик означает?
This means double point. There is one double point here, one double point here, and so on. And I can find string links whose closures are these links, and there is an n quasi-isotopy with one double point between these two string links.
Ну да.
But then for the next n quasi-isotopy, I will find a different pair of string links. So,
Вы можете то же самое взять, если вы очень захотите.
no, this is what I was explaining all the time. I cannot take lambda 2 and lambda 3 to be the same string link. This is what I cannot do. This is what I claimed last time, but now there was an example that it is probably
То есть
possible.
вам нужно хоть как-то соединить.
Yes, but this will be good enough actually. This will be good enough. So I change the string link. It's a different string link, but they have the same closure. So one can say it also in this way, that there is an equivalence relation on links which is to be closures of n quasi-isotopic string links. Links L and L prime are okay. N quasi-isotopic via string links if they are equivalent under the equivalence relation generated by ambient isotopy and the relation to be closures of n quasi-isotopic string links.
Ну, в общем, вы можете одну точку садить, n квазиизотопия, отследить на струнных зацеплениях, потом делать еще.
Да.
И если каждый раз, когда вы делаете струнное зацепление, вам что нужно отследить? Что это для замыканий?
Yes, just that they have the same closure. So first I represent my link as the closure of some string link. Then this string link is connected by an n quasi-isotopy to another string link. Then I can take the closure and take a different string link with the same closure. Then I can take n quasi-isotopy of string links.
Я не понял просто основное, зачем нужно отслеживать n квазиизотопию для этих
Струнных?
Нет, вы же для струнных можете отследить.
Не могу.
Почему?
Из-за всех этих примеров. Потому что я не могу засунуть вот этот вот, эти коричневые шары, я не могу засунуть в куб.
Нет, ну в данном примере, но вы можете дать такое определение, что можете засунуть.
Но я могу это сделать для каждой двойной точки по отдельности. И вот у меня действительно получаются такие кубы. Но проблема в том, что это разные кубы.
Ну, то есть,
если я хочу один
другое определение единое, то у вас вас не получится там импликация, потому что вы по одной точке собираете.
Ага.
И вот через стринг-линки вам нужно, чтобы теорема этого Масси, да, Массила какого-то была выполнена. Да?
Массуё.
Я уже сам
Да, да, мы к ней. We will return to Massuy's theorem after I finish this implication. It will be one of the last implications. So this is a formal definition. Two links are n quasi-isotopic via string links if they are equivalent under the equivalence relation generated by ambient isotopy and the relation to B closures of n quasi-isotopic string links. And we have such implication by lemma. Then we have the following implication. For all n, L and L prime are not separated by type n invariance of string links. So this looks strange because L and L prime are links in the 3-sphere. And I am saying that they are not separated by type n invariance of string links. This is not what you usually do with links in the 3-sphere. For them you have invariance of links. You cannot directly apply invariance of string links to them. So maybe I can take it in quotes and explain what this means. And the meaning is the same. There is the equivalence relation generated by ambient isotopy and the relation to be closures of string links not separated by type n invariance. Actually here I should add well defined up to PL isotopy. Maybe here I just put the box, which means well defined up to PL invariance of up to invariance of PL isotopy, or I can put something else in this box. And this is the definition of links L and L prime are not separated by type n invariance of string links and then box. Yes, I think I should write it here before the box of string links. And then box.
Простите, а к чему относится бокс?
Box means that I can put something else here, some property of such invariance. For example, well defined up to PL isotopy. Or it can be empty, this box.
как бы вы сказали, n-класс изотопных вот via string links по-русски?
Через струнное сцепление или посредством струнного сцепления? Не знаю, как лучше. Как вы считаете?
Мне пришло в голову через.
Хорошо.
Значит, вы что хотите?
Ну,
что значит они? Вы как угодно делаете струнизацию? Есть хотя бы одна.
Now I do the same picture about finite type invariants. I have no, I don't have such anything here. I don't have anything here, but I have links which are closures of string links.
И тоже такая же проблема, что нужно хоть как-то замкнуть, чтобы правильно сказать.
Yes. So these two string links are not separated by type n invariants. And these two string links are not separated by type n invariants. And these two have the same closure. And this means that L and L prime are not separated by type n invariants of string links. But also I might well defined up to PL isotopy. So this means that these are not separated by type n invariants, so defined up to PL isotopy. I can tell you an example. Actually, this is an interesting equivalence relation. It is natural. It is not just that I get something complicated in the proof. Actually, it's an interesting equivalence relation. So, example. We have the Bromian rings. Maybe I can draw them like this, actually. Okay, I believe this is the same as Bromian rings. And also I have the trivial link. So they are distinguished by the triple mu invariant, but it is not an invariant of finite type. So I can say that they are not separated by type 2 invariants, for example. And this is a theorem of Habir, that they are not separated by type 2 invariants. So he computed this somehow. But
Но он придумал последовательность. Это же не нужно доказывать. Нужно придумать последовательность, если не сепарировать.
no, this is in the usual sense. This is in the usual sense.
Нет, значит, не разделены. Это значит, что можно соединить в классе движений Хабира не очень сложных.
No, it's not equivalent. For string links it is equivalent. And for closed links it is not equivalent. And this is how he proves actually that it is not equivalent. For closed links.
Что надо?
So another theorem of Habira. Let me write it down. Well, actually, many authors here.
Ну, инварианты порядка 2 все расклассифицированы. Зачем там усложнять ситуацию? Их там не так много. Ну, вот взять и проверить.
Yes, let me write theorem. For n less or equal than 4 string links, two given string links L and L prime are Cn plus 1 equivalent if and only if they are not separated by type n invariance. Now this is for string links. Degree up to 4. No, this is checked only for n less than or equal than 4. For n equals 5, this is an open question. Even for string links. In one direction, it is obvious.
Да-да, я вспомнил, да.
So I think this was a paper by Yasuhara and Melikhov. They did n equals 4, and for n equals 2 and 3, previous people did. But this theorem is only for string links, and for links it is not true. For links it is just not true.
Когда n равно 3, то для обычного зацепления расклассифицировать вариант порядка 3 это уже очень сложно. Вот порядка 2 это просто.
Even for type 2 it is not true, because these are not separated by type 2 invariants, but they are not C3 equivalent. But not C3 equivalent. And this is also Habir's theorem.
Можно ли пару слов сказать, как Хабир показал, что что-то не C3 эквивалентно, если эти варианты подходят?
Ну, сейчас там какая градировка? Если был C3 эквивалентно, то он бы доказал, что не разделяются, да, вариантами порядка 2. Вот такая, да, формулировка?
So for string links in low degrees, these are equivalent things. And for high degrees it is an open question. For links, for closed links, they are not equivalent in low degrees.
В одну сторону, если не разделяются, да?
Yes, if there is
если можно перейти за 3 движениями, то можно, то, конечно, сохраняются варианты. Но какого порядка? Порядка 2.
Cn plus 1 equivalence always implies not separated by type n invariance. This is always for string links, for links. This is easy. We discussed this last time in pictures.
Да.
But the reverse implication is difficult and sometimes not true. For example, in this case. Misha, your question is good, but I don't remember well.
Чисто на случай, если бы сразу знаю.
We can, well, his proof is not long, we can look at it, but I think he uses some previous lemmas. I cannot say right now. We can look at it if you are interested. Okay, so how about string links? Petr Mikhailович, any questions about this?
Не, ну у меня есть вопросы, но я это самое, как бы не до конца это все понял. Ну вот ладно, пример кольца Боромева, там очень бедный инвариант второго типа, а C3 эквивалентность, конечно, нужна, потому что ты движениями распутаешься, а там C3 эквивалентность. Но это значит понятен пример.
But for string links, it is equivalent. So if you represent the Borromean rings as the closure of a string link, if you draw such a disk here, then for string links it's the same. So
просто для string link инварианты, внутри инвариант становится инвариантом второго.
Yes. Triple mu invariant, mu var 1, 2, 3. It is not a finite type invariant of links because it is even not well defined for all links with values in one group. It has values in different groups depending on the linking number. But if we consider it for string links, it is an integer which is well defined for all string links, and it is a type 2 invariant of string links. Yes, it separates And also this means that this string links, this one and this one, are not C2 equivalent. Because, well, so actually I can say more. So no matter how I represent the Borromean rings and the trivial link as closures of string links, these string links will not be separated by type 2 invariants. No. What am I saying? Will not be C3 equivalent. They will not be C3 equivalent because if they are C3 equivalent, then the closed links will be C3 equivalent. But they are not C3 equivalent. But for string links, C3 equivalence is the same as being separated by type 2 invariants. So no matter how I represent these two links by string links, these two string links will always be separated by type 2 invariants. But I can say more. Even if I do it like this. So this is the Borromean rings, and this is the trivial link. And I represent them as closures of string links, but possibly many times. Well, here, if I have C3 equivalence, then the closures will be C3 equivalent. And then the Borromean rings will be C3 equivalent to the unlink, which is not true, by Habir's example. So it means that at least if we are given such a sequence, then at least one of this pair is not C3 equivalent. But then this pair is separated by type 2 invariants. And this is precisely what is written here. This is the equivalence in the sense of this definition. So links are not separated by type n invariants of string links if they are equivalent under the equivalence relation generated by ambient isotopy and the relation to be closures of string links. So it means that they are connected by such sequence where these two are not separated by type n invariants, these two are not separated by type n invariants, and so on. But the Borromean rings and the trivial link are not equivalent in this sense. Well, I don't know how interesting it sounds, but I think so. There is an open problem that if L and L prime links in S3 are separated by type n invariants, and then are they separated by type R invariants of string links? So if you put n here, the same n, then the question is no. And this is an example. And the Borromean rings and the trivial link are not separated by type 2 invariants, but they are separated by type 2 invariants of string links because of this argument. No matter how we choose such a sequence, at least one pair will be separated by type 2 invariants. So it means they are not equivalent with respect to this equivalence relation.
Сейчас вы говорите, что вот будет место, в котором струнные зацепления различимы инвариантами второго порядка, но тогда это не отвечает на вот эту открытую проблему, потому что там вопрос вот всегда ли будут различимы инвариантами порядка n струнных зацеплений, в данном случае они различимы, то есть это не опровергает.
Да, но Брамеевская и тривиальная неразличимы, замкнутые неразличимы.
Сейчас, то есть это вот открытая проблема, да?
Ну, сейчас.
Я бы все просто, вы сказали, что вы сейчас ее решаете, или что она есть, и пример скорее подтверждает, что это так?
Сейчас, подождите, может быть, я действительно что-то тут напутал. Yes, I think it should be said no, yes. Not separate. Yes, this is the question. So this example shows that we cannot put n here. The Brownian rings and the trivial link are not separated by type 2 invariants, but they are separated by type 2 invariants of string links. So, yes, thank you. And as for this problem, so I think it is the problem of, more or less, the problem of Habegger and Melikhov. They state an informal problem which can be read in different ways. So last time I wrote down one possible reading, but this is another possible reading of the same problem which they have. So I think all these versions are open, but maybe this version is more interesting. Well, I don't know which version is more interesting, but it also makes sense. It's different and it makes sense.
И вот во второй строчке здесь подразумевается вот неразличимость инвариантов струнных зацеплений, это именно вот такая по цепочке.
Yes, these are links in S3, but they are not separated by type R invariants of string links. So it means such a. So here is the formal definition. Yes. So this relation to be closures of string links that are not separated by type n invariants, it is not transitive, generally speaking. We don't know that it is transitive. And we are just taking its transitive closure, but also with ambient isotopy. And this is how the transitive closure looks like.
Простите, я немного потерялся. Откуда первоначально... Сейчас. Каким образом вот то, что написано на правой доске, мотивирует вот определение через цепочку?
So one motivation for this definition was from this n quasi-isotopy, yes? Here, well, it's not a very strong motivation, but there is some additional motivation, because in this example so I can say that the Bromian rings and the trivial link are not, no matter how you represent them by string links, these string links will be separated by type 2 invariants. But there is also a stronger statement. Even if you not just represent them by a pair of string links, but if you do any such sequence. So you represent the Bromian rings by the closure of one string link, then there is another link which is represented in two different ways by a string link, and so on. Then it is at least one such pair will be separated by type 2 invariants. It is a stronger statement than just saying that the Bromian rings and the trivial link are not closures of any pair of string links which are not separated by type 2 invariants.
То есть вот мы, значит, предполагаем, что по цепочке есть инвариантность относительно инвариантов структурных зацеплений, в смысле неразличимых этими инвариантами, тогда есть C3 движения.
Yes, for string links, these are equivalent to C3 moves, and if we have C3 moves here, then we also have them here, and then the Bromian rings would be C3 equivalent to that link, which is not true. So it's a stronger statement, and maybe it's interesting that such a stronger statement exists, and then there is a problem. I don't know how good motivation it is. Okay, so can I move on?
Пару секунд. Да, все.
So the next implication is the following. For all L and L prime are not separated by So I think here I should put a tilde, and I will explain what this tilde is. I think last time I wrote A and B, and this was A prime and B prime. Maybe it's better to do it like this. So these are A and B, and here is A prime and B prime. I will recall what they are in a moment more. Maybe I write it here. So A prime is A connected sum with KB, and B prime is B connected sum with KA. So Ka is a totally split link whose components have the same node types as the components of A. This was from last time. So A prime and B prime are not separated by type n invariants. By locally additive type n invariants of string links. And this will be another lemma, maybe I call it lemma 2. But before I prove it, let me finish this diagram. So here we will apply theorem 3, which I stated last time. And the implication is that for all n, A prime and B prime are not separated just by type n invariance of string links. And then I can write that for all n, A prime and B prime are not separated by type n invariance of links. Just by type n invariance. And from this we can conclude that A and B are PL isotopic to links which are not separated by finite type invariance. And this is what we wanted. We wanted to show that if A and B are topologically isotopic, then they are PL isotopic to links which are not separated by finite type invariance. And the last arrow is trivial because A and B are PL isotopic to A prime and B prime. This is how we define them. These are totally split links, so they just consist of a local node on each component. And the previous implication, if A prime and B prime are not separated by type n invariance of string links, then they are not separated by type n invariance in the usual sense. Because if we have such a type n invariant of links which separates them, then we can define an invariant of string links using this invariant of closed links. Namely, so V is an invariant of closed links, and we define an invariant W of string links by W of a string links equals V of its closure. And this will be a type n invariant, and it will separate A prime and B prime. So let us prove lemma 2. Okay? So what are we given? We have our links A and B, and we know that they are not separated by type n invariants of string links well defined up to PL isotopy. So it means that there exists a sequence like this. A is a closure of a string link L, then L is equivalent, yes, L1 is equivalent to L2 in the sense that they are not separated by type n invariants well defined up to PL isotopy. Then the closure of L2 is some link, I don't know, lambda 1. And then we're represented by another string link, and it is equivalent in the same sense to lambda 4, which is whose closure is lambda 2 and so on. And in the end, lambda M is B. And this is what we are given.
А вот в заключении там утверждение уже не про цепочку, да?
I think this conclusion is also about a sequence.
А в следующем после теоремы 3?
And this is also about a sequence. But here we apply theorem 3 just in each of these stages. But so the sequence disappears here. This arrow is specifically about removing the sequence. So,
Да, понял.
do you want to discuss this arrow?
Всегда да.
Okay. So let me briefly say that if we have such a diagram, and these are not separated by type n invariants, so of string links, then this will be not separated by type n invariants of links. Because if they are separated by type n invariants of links, then this type n invariant gives us an invariant of string links by this formula. So these are not separated by type n invariants, and that means that A and B are not separated by type n invariants. So we will remove this sequence in the end, and now we have to deal with this sequence. So this is what we are given, and let me also say what we want to prove. So we want to obtain another sequence of this sort, but here instead of A, we will have A prime, and instead of well-defined up to PL isotopy, we will have locally additive. So we want to replace this well-defined up to PL isotopy by locally additive. And we cannot just replace it like this, but if we also replace A by A prime and B by B prime, then we can do it. So we want to construct such a sequence with A prime and B prime and local additive invariants. And there is the following lemma which we proved essentially last time. It was stated slightly differently, but let me state it. learn this. So if if we have two links, L prime are links, that doesn't matter here, links or string links, links or string, which we are going to use. Well, okay, links or string links. Such that KL equals KL prime. So I think last time we applied this specifically to A prime and B prime, but the only thing which we used about A prime and B prime was that their K totally split links are equal of term point isotopic. Okay, and L and L prime are not separated by type n invariance. Well defined up to pure isotopy. Then L and L prime are not separated by locally additive type n invariance. Actually, it was if and only if. I can write here if and only if. So suppose that and this is a new set. L and L prime are not separated by type n invariance well defined up to PL isotopy if and only if they are not separated by locally additive type n invariance. We can claim this assuming that KL equals KL prime. And the proof was that if we have, well, one direction is obvious, because a type n invariant well defined up to PL isotopy is locally additive. A type n invariant well defined up to PL isotopy is always locally additive. If it is well defined up to adding local nodes, we just add 0, which is okay. And in the other direction, if we have a locally additive invariant V, then V is locally additive. Then we can construct an invariant which is well defined up to PL isotopy. We can define it by the following formula: W of L equals V of L minus V of KL. If V is locally additive, then this will be invariant under PL isotopy. And so this is how it is proved. We just need to take care of these parts, but they will be equal because of this hypothesis. And actually, yes, I think I want to modify. This is what we proved last time, but I want to modify it a little bit. And here, so it's enough to assume that KL and KL prime are not separated by type n invariance. Because even by locally additive type n invariance, because we just need this to be equal to V of KL prime. I write here W of L prime equals V of L prime minus V of KL prime. If these two are equal, then these two are equal by hypothesis. V is locally additive, and we assume that they are not separated. And then these are equal, and this is so.
Вы доказывали сейчас в какую сторону?
I was proving in the interesting direction. If they are not separated by local additive invariants, then they are not separated by invariants well defined
Это
up
как
to
раз
L
интересно, потому что любой инвариант на вероятности изотопии локальной DT.
Sorry, you're right. This direction.
То есть теперь мы хотим установить, что V не меняется, а знаем, что W не меняется и вот K.
Yes, you are right. Yes, we want to prove that these are equal, and we know that these are equal. Yes, and also we know that these are equal. Yes, thank you. Okay, so we have such a lemma, and now we want to apply it essentially just on each stage. We want to apply it to these string links. But there is a little problem, namely that we want these corresponding totally split links to be not separated by type n invariants. And here we generally don't have this in the original sequence. So we want to achieve this somehow.
Что должны получить?
We just want to get this condition somehow. If we knew that this condition is satisfied for L1 and L2, for L3 and L4, then it follows trivially just by using this lemma. But so far we don't know that this condition is satisfied here. This Li's can have different local nodes, and this is why actually we have our A prime. So A prime was A connected sum with B, with KB, and A prime is A connected sum with KB, B prime is B connected sum with KA. And the reason why we do it is that the local nodes here are the same as the local nodes here. So KA prime equals KB prime. But there is a little problem that this construction only works in the beginning and in the end. So for A and B, by passing to A prime and B prime, we indeed achieve that they have the same local nodes. But we also want the same local nodes at each moment, at each stage. So we have to do something slightly different. Well, this we do anyway in the beginning and in the end, and we can. So we have this L1 here, and then we just add to L1. We add this KB.
Я бы сложил с K от всех верхних зацеплений.
Okay, this is one possible approach, but this depends on the length of this sequence and on the choice of these links. And this is something we don't want, because if instead of A prime and B prime we will get something depending on n, then we will have a problem in the end. So we want to do it independently of these links. But yes, we have this last link, L2n or something like this, whose closure is B. And we can add to this string link, we add k of L2n. It is essentially the same as KB. And of course here we can do the same. We have this L2n, and we can add to it KL1. But now we have to deal with the links in the middle. So we have Li, and what do we add to Li to get the same local nodes as in these two links? So these two string links, they do have the same local nodes. but we want to do to achieve that also the intermediate one have the same local nodes. But actually we don't need exactly the same local nodes. We just need the same local nodes up to type n invariance. And we can do this, so we can consider the following L. Yes, I think I just tried here Li prime, and this Li prime is going to be the following. So I take K of Li, this is some totally split link. I can consider its class up to Cn equivalence. This is totally split string link. I can consider its class up to Cn equivalence, and it has an inverse up to Cn equivalence. Because string links up to Cn equivalence form a group, Gusarov's group. Yes, so maybe I should also put the class here, and then this will be just this KL1 connected cell with KL2N. So this is this last part is the same as we have here and here. It has the same local nodes as here and here. So for Li, we subtract the local nodes that it had and add the local nodes that we want.
Напомните, пожалуйста, вы говорили, почему по модулю CN струны зацепления образуют группу?
It's a theorem of Gusarov. It's not trivial. So I was saying that this group is nilpotent and not abelian. Okay. Here it's actually these string links are totally split. So it's essentially the case of nodes. And in the case of nodes, it is even abelian. Yes, so this group is even abelian. It's non-trivial. I have to use it. I cannot explain the proof now. So we subtract the local nodes that we had in Li. And we can do this not exactly, but up to Cn equivalence. And up to Cn equivalence means that type n invariance will not. It will be okay for type n invariance. And then we add
n-1, n-1. То есть они же отличаются.
L-1.
Индекс C на 1 больше, чем порядок инвариантов. В общем, там Cn плюс 1.
Cn plus 1, yes. Cn plus 1, yes. And here I think we also have something L2 I minus 1 and L prime to I. They need to have the same closure, maybe lambda I. L1. No, I think 2I and 2I plus 1. Yes, so these two need to have the same closure. So if we do this construction independently for these two links, then we can get the problem that they do not have exactly the same closure, but they just have closures which are the same for type n invariance. But this is not okay. So we do this construction for one of these links, and we get, so this is a totally split. Yeah, maybe I should use some different letter here. Because here I want to add. Here I should write what we had, lambda 2I, and then connected sum with this fi, or f2i. And here I write lambda L2 I plus 1 connected sum with the same F2I. So I'm not going to construct a new F2I plus 1, but I take the same F2I. And so these two links, these two string links, they had the same closure. And then after taking this connected sum, they will still have the same closure. So we're okay with the closure, and here we will have the equivalence modulo type n invariance, just because this is how we construct this nodes or totally split links. So these are totally split links, or essentially local nodes, where only the links are the same. We're only changing the local nodes, and we are changing the local nodes so that type n invariants don't notice this. And this is what we wanted to do. Now we get such a sequence of string links, so that they have the same closures here, are not distinguished by. Yes, so I think so the reason that they are not distinguished by type n invariance here is because of this lemma. And this lemma says that we had some pair of links which are not distinguished by type n invariants, which are well defined up to PL isotopy. Now we are adding to them different actually local nodes. I don't know, somewhere here I should write. The next one goes here. L2 I plus 2 connected sum with F2 I plus 2. So here the reason that they are not distinguished by locally additive type n invariance is this lemma. L2I and L2I plus 2, L2I plus 1 and L2I plus 2 were not distinguished by type n invariance well defined up to PL isotopy. And these local nodes are also not distinguished by type n invariance. So this lemma applies. The way we chose these local nodes is that we cancel all local nodes that are here and all local nodes that are here. And instead we add the local nodes which are here and here. So after this addition, we must have the same local nodes here and here, up to type n invariance. And this is what the lemma wants. I should say again, yes?
Расскажите, пожалуйста.
So in the beginning, we are given a pair of links which are not separated by type n invariance well defined up to PL isotopy. Then we are adding to them local nodes such that we cancel the local nodes which we had in these links, but instead we add the local nodes which are here and here, and they are the same here and here. So now after this connected sum, we have the same local nodes here and here, up to type n invariance. Not exactly the same, but up to type n invariance, because we used this inverse here. We do this cancellation only up to type n invariance. It's not exact cancellation, but only cancellation up to type n invariance.
Значит, пока знаем, что k от вот этих двоих эквивалентно вот полему.
Yes, k of this equals k of this, and this is exactly what we want. Because now these links are not separated by type n invariance, well defined up to PL isotope. Well, we knew this about these links, but these are local nodes, so it's still, they are PL isotopic to this is PL isotopic to L2 I plus 1, and this is PL isotopic to L2 I plus 2. These are not separated by type n invariants well defined up to PL isotopy, and then these are also not separated by such invariants. So we can apply the lemma to them, and we get that these two links are not separated by locally additive type n invariants. And this is exactly what we wanted. So we obtained that A prime and B prime are not separated by locally additive type n invariants of string links, which means just such a diagram. Okay? So only theorem 3 remains to be proved. Yes? And what is about time?
Ну, так, вы переделали всюду в вашей последовательности условия того, что замыкание струнных сцеплений n эквивалентно или n квазиизотопно, но при этом раньше было понятно, а сейчас как-то меньше понятно. Но зато раньше было неправильно, а сейчас правильно. Но может быть, что вы как-то это самое все-таки не будете так уж совсем произвольно закручивать концы, потому что, наверное, как-то можно более экономно это все сделать. Зачем вам нужно? Ну, хорошо, вы сейчас доказали. Вот помните, вы пример привели, и вы там уж совсем плохо замыкали концы.
Yes, because of this example, I think it is difficult to simplify this. Well, if you have an n quasi-isotopy with two double points, then you have a sequence of balls for a first double point and a sequence of balls for a second double point, okay?
Yeah.
Outside of the first big ball, you have some disk, two-dimensional disk, which will give you the string link. And outside the big ball for a second double point, you have a disk. But now you want to find a disk outside the union of these two big balls. Maybe you can do it, but I cannot do it, because the union of two balls can be very complicated. I don't know how to describe such unions of two balls. And then you can have a union of three balls.
Нет, ну вот в вашем примере, вы когда это самое, вы сказали, что вы хотите показать примеры, хотите замыкать как вам угодно. И замкнули так, что из 3 компонентов получилось 2. Но это просто был пример. Да. Это же не нужно носить.
Да, это был пример, да.
Но вы напрасно этот пример привели, потому что я самое. Ну, этот пример может что-то и показывает, но.
Но он показывает, что так просто исправить не получается.
Нет, но вы показали пример, когда вы из 3 компонент оставили 3. Но когда вы из 3 компонент сделали 2, я не понял.
Но это была вспомогательная конструкция, чтобы доказать, что у этого струнного сцепления нет локальных узлов. Потому что если бы у него были локальные узлы, то и у любого вообще замыкания, даже самого странного, тоже были бы локальные узлы.
Ну, сейчас пишу в одну сторону только.
Да.
Нет, ну допустим, что. Нет, ну мне все равно непонятно. Ну ладно. Доказали, хорошо. Просто зачем давать определение локальных узлов и при этом портить концы зацепления? Ну, вы, конечно, больше найдете информацию, если вы будете портить концы. Но если вы ее не найдете, ну значит там нет локальных узлов у струнного зацепления. Нет, ну вот зачем вы сделали 2 компоненты? Вы замкнули, и что? Ну вы не построили там локальный узел, а по-другому он всегда там оказывался, что ли?
Но это была вспомогательная конструкция. Ну давайте.
Нет, не надо ее повторять, я просто не понял логику.
Ну смотрите, значит.
Вы хотите отследить, есть ли локальные узлы в исходном зацеплении. И вы делаете замыкание всеми возможными способами. И до всех возможных способов, если хотя бы есть один способ без локальных узлов, значит там их не было.
Да. Вот и все. Только для этого нужно было делать ударное замыкание.
Ну хорошо, ну а если бы вы для любого для всех странных замыканий ничего бы не нашли, вы же не можете сделать отсюда никакой вывод? Или можете?
Не могу. Но мне нужно было пример обосновать как-то до некоторой степени. Но я попытался это сделать. Но я не провел вычисления там, поэтому я его до конца не обосновал.
У вас есть теорема, что если для любого замыкания отсутствуют локальные узлы, то их там нет. Если они там есть, то в какую сторону работает? Если там есть локальные узлы, то есть замыкания, в которых есть локальные узлы.
Если в струнном зацеплении есть локальные узлы, то и во всяком замыкании есть локальные узлы.
Ну, да. А теперь вы говорите наоборот. Значит, если нет ни в одном замыкании локальных узлов.
Если в каком-то замыкании нет локальных узлов, то значит уже и в струнном их не было.
А есть такой пример, когда только на странных замыканиях появляются локальные узлы, а на нестранных их нет.
Вот это был тот самый пример, который я рисовал.
Ну ладно, нет, ну это определение, значит, определение очень сложное, только для знатоков. Ладно.
Нет, ну пример в чем состоит, что в струнном зацеплении нет локальных узлов, а после замыкания появляются локальные узлы. Но это удивительный несколько пример. Я долгое время думал, что такого не бывает, и даже пытался этим пользоваться. Но потом понял, что это неверно. Но эта ошибка напрямую связана с той ошибкой, которую в прошлый раз вот вы нашли с Мишей.
Ну ладно, вы тогда после перерыва будете что-то доказывать.
Да, значит, осталось...
Я, наверное, потом послушаю.
There remains just theorem 3 to be proved, and I think it's time to make the break. Yes. All right, let us continue. So, I want to prove theorem 3, which I stated several times already. So it says that for each n there exists an R such that if string links L and L prime are not separated by locally additive step R invariants, and then they are not separated by step N invariants. And this theorem will be a corollary of another theorem, proposition. And the theorem 3 prime. The same hypothesis and the conclusion is different. Then they are CN equivalent. CN equivalent. It doesn't matter here, but yes, maybe I should write CN plus 1 equivalent. Then theorem 3 will follow from this, because we know that Cn plus 1 equivalence implies not being separated by type n invariants. And this is what I showed last time using pictures for small n. Yes, I should say that this R depends only on n and the number of components. So the string links have m components. Okay, and I think we are more or less ready to prove this using some notation from the proof of Massuyot's theorem. So, in the proof of Massuyot's theorem, we had the monoid of string links Gn was L modulus Cn equivalence. Then we had the group ring, the monoid ring. And in this monoid ring we have two ideals, Vn and Wn. So maybe I can write here that the group ring of this Gn is Zl modulo Wn. So Wn, in other words, Wn is generated by all formal differences L minus L prime, where L is C n plus 1 equivalent to L prime. Sync n plus 1. No. Yeah. But Vn is generated by all singular links with k double points. N double points. I think I'm confusing about n and n plus 1. If you have C1 equivalence, that should be W1, and V1 is one double point. Yes, everything is correct. So this is Vn is generated by all singular links, singular links with n double points. And here we understand it as a formal linear combination of non-singular links which are obtained by all possible resolutions of this singular link. So corresponding to each sign, to n, we have n double points, and if we fix n signs, then we get a resolution of the singular link into a non-singular link. And we take the sum over all signs, but I think that we should also put these signs here. The product of these signs, and then this non-singular link.
То есть слева от черты на самом деле это должно стоять, вот эта сумма?
Yes, formally speaking, this sum should be here, yes. But by this I mean that I identify the singular links now with such sums of non-singular links. So V stands for Vasilyev because these are finite type invariants or Vasilyev invariants. More specifically, if you have, if V is a type n invariant, you can understand it as a map from L to some abelian group G. But also it extends to a homomorphism of this monoid ring into G. This is a homomorphism of abelian groups, of course. Just additive homomorphism. And so this is V, this can be called V bar, and yes, maybe this works for every invariant, but V bar, V is a type n invariant if and only if V bar vanishes on Vn plus 1. And because it must vanish on singular links with n plus 1 double points, and it means that it must vanish on some such sums, actually. So we had there is obvious inclusion Wn lies in Vn. Well, it's not completely obvious, but it's proved easily by pictures, like I tried last time. And instead of the other inclusion, we have V q times n minus 1 lies in delta n plus Wn, where delta is the augmentation ideal.
Там где-то Q должно быть в последнем включении.
Yes, thank you. This is Q. And so this inclusion is non-trivial theorem, is the most important probably theorem of Abiro's paper, or at least it is one special case of the most important geometric theorem. And we are not able to prove it. It's complicated. It takes many pages. Maybe it's not very difficult. Every step is clear, but there are many steps. And so we have to use it, and also we have we had some lemma about nilpotent groups and their dimension series, which must terminate at some finite step. And using this lemma, we proved the following. We proved that 1 minus, using this inclusion and also the lemma about the dimension subgroups, we proved that 1 minus L intersected with V Q times N minus 1 lies in Wn. So this is almost a reverse inclusion. It is just restricted to such differences. So one is the trivial link here. So instead of considering differences of any two links, we consider differences of the trivial link and some other link. But actually it's so these are two-sided ideals. So I think we can also write it in this way: L minus L, which means this means that it is the set of such formal differences where L and L prime are in the monoid L. This doesn't trivially follow from the previous assertion, but it follows with some work. I didn't tell this implication last time, but you said that it is not necessary. I can tell this if you want.
Да, если что-то сказал.
Okay, so this is more or less what we had the last time. And yes, so this inclusion, from this inclusion we got Moussuille's theorem, which says that for each n there exists an R such that if string links are not separated by type R invariants without local additive, then they are not separated, then they are Cn plus 1 equivalent. So this is almost what we want. We almost proved theorem 3 prime last time, except that it didn't have this locally additive in it. Now we just want to include local additive into Moussuille's theorem. And so we need some additional ideals here, which correspond to the condition of local additivity. So what is the condition of local additivity? The condition is that the value of our invariant under the connected sum with totally split link equals V of L plus V of K. So another way of saying that is that V, or this extension of V to the monoid ring, vanishes on formal differences of the form. Maybe I can just write Lk because it is the product in the monoid. Lk minus L minus K, this should be 0. And this is the same equivalent. For again where K is totally split. Now this will be equivalent to the following condition. V bar vanishes on the products of the form L minus 1 times K minus 1. and V bar of 1 equals 0. 1 is a trivial link, so V bar must assume value 0 as a trivial link. And why is this? Well, L minus 1 times K minus 1 is Lk minus L minus K plus 1. Exactly what we had here, but plus 1. So I think this direction is clear. If V bar of 1 equals 0, and V vanishes on such differences, then it vanishes on such Lk minus L minus K. And conversely, I think we only need to prove that V bar of 1 equals 0, because if we know that it is 0, then this will be also 0.
А это за 1 плюс 1 равно 1?
А?
Это за 1 плюс 1 равно 1?
Yes. So if L equals 1 and K equals 1, then Lk minus L minus K equals 1 minus 1 minus 1, which is negative 1. And V of this must be 0, because V is additive. V is a group homomorphism, so we can this minus can go out. V of minus 1 equals minus V of 1 equals 0. Okay, so this direction then also follows. Okay. So yes, we have in such a product L minus 1 times K minus 1, and we have our augmentation ideal delta, which is generated precisely by the products, precisely by the differences L minus 1, where L is in the monoid L. And of course we can consider in the monoid L, we can consider the submonoid K, which consists of totally split string links. And then we have the augmentation ideal of this monoid ring. I will call it lambda because it corresponds to local nodes. These totally split string links are really local nodes. Now this lambda, it is an ideal of the monoid ring Zk, but it is not an ideal of Zl. If we multiply a totally split string link by some string link, take the connected sum, it is not totally split anymore. But lambda delta will be an ideal of Zl because we can multiply. So if we so this will contain actually such differences, L minus 1 times K minus 1, and it will be generated by such products, because lambda is generated by differences of the form L minus 1 and delta is generated by differences of the form K minus 1. So their product is generated by such products. And we can multiply this product on the left by another string link L. And this will still be in this product, because this is the same as L prime L minus L prime times k minus 1, and this still lies in delta, and this still lies in lambda. Sorry, I confused. This is lambda and this is delta. So this still lies in lambda, this still lies in delta, because delta is an ideal. So we get that it is a left ideal, but also it is a right ideal, because we can write that delta lambda equals lambda delta. And this is because local knots commute with, when you add local knots, you can add it, you can add them on the left or on the right. It doesn't matter, because you can push them through the string link to the other side. So we get that it is an ideal, two-sided ideal. So I think I should have said that these products additively generate delta lambda, because the augmentation ideal is additively generated by such differences. When you say that an ideal is generated by some elements, what do you usually mean? Additive or additive and multiplicative?
Такие скобки, это вроде линейно, то есть аддитивно.
Okay, so then okay. So the reason to make this, to put it on this way, is because this extension is not a ring homomorphism. So generally speaking, its kernel is just a subgroup. It doesn't have to be an ideal. So we have to be careful. So the claim is that, where can I write it? Maybe here. We use locally additive if and only if V bar of 1 equals 0 and delta lambda lies in the kernel of V bar. So even though the kernel of V bar is not an ideal, I think we proved this because we used only additive generation. So here, this is different. This was not used in this claim.
Это очевидно или сейчас будете доказывать?
I think I already proved this. because here we had that. So locally additive means this condition, and it was equivalent to this condition. So V bar of 1 equals 0, and also V bar vanishes on such products, but such products additively generate delta lambda, and so they generate it as a subgroup, and so we have this. Okay, so now in addition to our favorite ideals Vn and Wn, we also have this delta lambda, and so we want to describe the quotient, this monoid ring modulo Wn plus delta lambda. So this is our goal, to describe this quotient ring. So we have our monoid L and the submonoid K. Then we have L modulo the Cn equivalence, which is Gn. And similarly we have K modulo the Cn equivalence, and we call this Hn. So Hn is a subgroup of Gn. So it's a group of a totally split string links modulo Cn equivalence. So Hn is commutative because nodes commute with each other, and moreover it lies in the center of Gn. It commutes with every, a totally split link commutes with every string link. So it lies in the center of Gn because K connected sum with L is the same as L connected sum with K. K is totally split. So in particular it is a normal subgroup. Since it commutes with all elements, it is normal. So we have the quotient Gn modulo Hn, and we can call it Qn. But actually I claim that it is a direct sum, direct product. So, and this is because we also have a map from Gn to Hn. And this map associates to a link L, or to the Cn equivalence class of the link L. It associates this totally split link KL, or rather it's Cn equivalence class. So here one has to be a little bit careful. We need to prove that if two links are CN equivalent, then their associated totally split links are also CN equivalent. But I think this is more or less clear because here we look separately at each component, and if we had
Да, то есть либо каждая компонента меняется в соответствии с CN. Значит,
yes, if it is a self-CN equivalence.
Вот CN эквивалентность это все это какая-то явная гомотопия. Можно, то есть если с обеих концов есть гомотопия с зацеплениями, где каждая компонента не пересеклась, но с остальными зацепилась, то
Well, this is so there is self-CN equivalence. It is defined by CN moves which involve only one component. And it is related to invariants of type n, and so on n. Namely, such invariants are invariant under self-CN equivalence. So it's clear that if two string links are self-CN equivalent, then their associated totally split links are also CN equivalent and self-CN equivalent. But what if we have a CN move which involves two different components?
вот оно как раз не важно, потому что когда мы отодвигаем все компоненты друг от друга без их самопересечений, то мы в любом случае позволяем им друг с другом пересекаться при создании К. То есть К не меняется при пересечениях разных компонентов. Вот. При этом при создании КЦН не фигурирует.
Yes, if in the CN move we just remove one of the strands, then the remaining strands will be also. I think.
Да, вот берем значит, m копий L, для каждого прокручиваем нашу CN эквивалентность, и получается убирая все компоненты, кроме одной, и получается CN эквивалентность для K. Ограничение CN эквивалентности на компоненты CN эквивалентность.
Yes, it is. I think it is just ambient isotopy. If you remove one strand, then this what you had in the CN move, these two pictures will be just ambient isotopic always. So, for example,
с этим движением меняет перекресток, который так любой узел можно было бы распутать.
Yes, but if you remove one of the components, then the other component is.
Может быть одна и та же компонента.
Yes, if it is one component, then it is self-CN equivalence, and then it is clear. I'm speaking about CN moves which involve different components. If it involves only one component, then yes, then it is clear. But what if?
Для разных да, объемов, да.
And if it involves different components, then we are removing one of the strands. Maybe it is like this. And the other picture was like this, I think. Yes? No. I forgot, what was the definition?
Именно так, да.
Okay. Well, if we remove this one, it's clear. If we remove this one, yes, we can do it. And if we remove this one, also we can. And I think it can be, it's true for all CN moves. Yes, okay, so we have such a map, and it is a homomorphism, because it takes connected sum into connected sum. So the kernel of this map must be a normal subgroup. Maybe I call this kernel Qn, and I don't write it here. So this Qn is a normal subgroup, and Hn is a normal subgroup, and they have trivial intersection. Because what is their intersection? Hn consists of totally split string links, and Qn consists of those string links whose equivalence, CN equivalence class lies in the kernel of this map. So their KL is trivial. Their KL is CN equivalent to the trivial string link. So we have Hn already consists of the totally split ones, and now we know that KL is trivial up to CN moves. But KL is the same as L. So if L lies here, then KL equals L. And KL is trivial up to CN moves. This means that L is trivial up to CN moves. So we get 1.
Как-то я это понял.
Maybe I should write K, because I previously denoted such totally split links by K, so then K equals K, and this looks better. K equals K.
Да, всё, понятно.
Okay, so we have two normal subgroups whose intersection is trivial, and this means that we have a direct product. Gn is the direct product of Hn and Qn.
Это, получается, было доказательство существования разложения на глобальную и локальную часть, которая вообще, то есть прям полное доказательство. Да?
Well, it's a different decomposition. It's really a decomposition into the local part and global part and local part, but it's different from what I said in the beginning of the talk, because here these are string links up to CN equivalence, and yes. So how this decomposition looks geometrically, really. This Hn consists of local nodes. And how can you imagine an element of Qn? Well, you actually fix any representative of an element of Gen. You fix any string link up to local nodes. So in this theorem about decomposition to the local part and the global part, we had that every link or every string link can be uniquely represented as a connected sum of a local part and a global part. And here, for the global part, we can take any string link which is equivalent to our string link up to PL isotopy, up to adding local nodes. Because we have a group, these local nodes can be inverted in this group, and so it doesn't matter.
Can be
inverted, and so it doesn't matter which representative we take as our global part. So in this decomposition, the global part can geometrically have local nodes, and it doesn't matter because we can just cancel them.
И отсюда никак просто не получается однозначность.
It's completely different theory. This is up to CN equivalence, and it's a product of groups. And if you consider just links up to ambient isotopy or string links, better string links, then I think it will be a product of monoids. And they are, well, probably there is some map in one direction from that decomposition into this decomposition, but certainly you cannot reconstruct from this decomposition, you cannot get that decomposition, because they exist, these two decompositions exist for completely different reasons.
Понял, я просто хочу понять, что не сработает в доказательстве.
This decomposition exists because of a group structure, because there exist inverses, and that decomposition exists because of geometric arguments with cut and paste. You know, when you have intersection of two balls, then there is on the boundary of each ball there are many circles which are the intersections, and then there is the innermost circle, and you do some surgery along the innermost circle and so on. So the proof of that theorem is based on this sort of arguments. It's purely geometric, and this is almost purely algebraic.
Сейчас мы все-таки у нас, если брать не с точностью до CN, то мы знаем, что HN совсем коммутирует, и остается выбрать остается установить существование второго слагаемого. Но аналог HN совсем коммутирует. Ядро есть, получается. То есть для моноидов, получается, не работает теорема, что если есть там, что если есть гомоморфизм и подгруппа, которая отображается новым изоморфно, то будет произведение. Получается, этого нет.
We don't have subgroups in monoids. We have submonoids, and you know there are normal subgroups, and for submonoids, it's how do you construct the quotient?
Вот про аналог Ашен мы уже знаем, что он просто коммутирует совсем. Что про ядро нужно понять, что про ядро.
You think it's possible to prove it just like this?
В общем, простите, да, там было кажется, но... Элементы ядра можно... Сейчас. Да, в общем, канонической форме произведения не получится подвести. То есть, если вот мы возьмем Декартово произведение ядра и H, аналог H, то вот произведение двух вот пар не удастся привести в вид пары, потому что для этого нужно переставить... нет, переставлять можно, это элемент H совсем коммутировать, по-моему, можно так. Сейчас только вот единственная ситуация.
Okay, maybe I have to think about it. Maybe this is a good question, because I thought that it is non-trivial. Well, how about this example which we had in the beginning? So these two decompositions for links and string links are completely different, and with your argument they are probably not going to be different. How can they be different with your approach?
Сейчас, кто будут разные?
So we had the decomposition for string links into the global part and the local part, and for links.
Для просто зацепления я ничего не говорю, я чисто для струн.
But wouldn't your argument work for links as well? What is the difference?
Ну, в принципе, операция, то есть, нет операции.
Well, we have the operation. For totally split links, there is a well-defined connected sum. And also there is a well-defined connected sum of any link with a totally split link.
Такая операция есть, но... Сейчас.
Well, okay, maybe we think about it later. It's a very interesting question. Well, so anyhow, we have such a decomposition. And now let us. So maybe I should say that. So Habira already did everything that we are doing in the case of nodes. So in the case of nodes, he proved that. So Habira's theorem for nodes. So he proves that Cn plus 1 equivalence is equivalent to being not separated by type n invariance, and also to not being separated by locally additive type n invariance. And he proved it in the same way, so I think this is obvious. Then there is this arrow which is non-trivial, and this is also easy. So this is completely obvious, this is easy, and this arrow is non-trivial. So how did he prove this arrow? He considered the homomorphism from this monoid of nodes. Yes, so there is a group monoid, and of course, yes, there is a group ring of this group Gn, which is K modulus C equivalence. I don't know. Here we have nodes, so I write K. But then he considers the mapping to Gn. In that case, Gn is abelian, and such a map actually exists. So you send every element G, element of this group, into itself. And this extends to a map of this group ring because, well, what is G? G is some node. Okay? So every node goes to itself, and what is K plus L? Okay, it's a formal connected, it's a formal sum, but you can send it to their connected sum. And it works. It's a well-defined map, it's a group homomorphism. And it is actually, this composition is a universal type n environment, as he proves. And then we had our delta lambda, and in his case delta lambda. And in his case, I think he had just lambda squared, because he has nodes and no links. And I think he proved that lambda squared, well, somehow he found lambda squared somewhere here, and this, so I think maybe it lies in the kernel of this map, and this allowed him to prove this arrow. And so we want to do something similar, and then let us consider the following ring. So Rn will be the group ring of Qn plus Hn. Yes. So additively it's just a direct sum. But what is the product in this ring? Well, the product is the following. So I take R1 H1 and then multiply it by R2 H2. And this gives me R1 R2 because this group ring is a ring. And here I should write H1 to the power augmentation of R2. So H2 to the power augmentation of R1. So here Hn is a subgroup of Gn. Hn is abelian, so maybe it makes sense to write it additively. but also it is a subgroup of Gn, and here we have products of elements of Gn, so maybe it's better to write it multiplicatively. Well, anyway, I'm writing multiplicatively, even though it's abelian. So I think it has to be checked that this is really a ring. So we need to check distributivity. Or you don't want me to check it.
Секунду. Понятно.
Do you believe it? Andreas doesn't want me to check distributivity. Do you want me to check the distributivity? I defined a ring, and
Well, up to the moment I didn't understand the definition, so distributivity check doesn't really make sense.
do you want me to repeat anything?
If you can repeat the definition, please.
So we have the monoid of string links, and we have the submonoid consisting of totally split string links.
Okay.
Then we consider the quotients of both by Cn equivalents, and this will be groups, a group Gn and its subgroup Hn. This Hn will be in the center because local nodes commute with any string link. You can push a local node from one side of the string link to another side of the string link, just along the strand.
I know.
So this Hn lies in the center. In particular, it's a normal subgroup. But on the other hand, we can define a map from Gn to Hn, which simply sends every link to this totally, or every string link, to this totally split string link, which is just formed by the components considered separately. And this map is well defined up to Cn equivalence, which can be checked. And the kernel Qn of this homomorphism, it's easy to see that it has, so it's a normal subgroup since it's a kernel. And it's easy to see that it has trivial intersection with Hn. And so we get the decomposition of our Gn into a direct product. And this is actually similar to what we had in the beginning today, because it's also a decomposition into a local part and a global part. Hn is the local part, it's the totally split string link, so it's really local nodes which are in our string link. And Qn is the global part. So it's a third type of decomposition, but it's different from what we had before, because this decomposition, it's not based on decomposition into prime nodes, it's based on the group structure up to Cn equivalence. And then we discussed with Misha exactly how different these decompositions are, and I think we still need to think about it. We didn't reach any definite solution. And now I want to define a ring based on this decomposition. So my group Gn is decomposed as Qn times Hn, where Hn is the local nodes and Qn is the global part. And now, well, Hn is abelian. It even commutes with, it even lies in the center. But in particular, it's abelian. So I can do the following strange construction. I consider the group ring of this group Qn, and I add the abelian group Hn separately. This will be a group, an abelian group, but I also want to put a ring structure in it. Namely, I define multiplication as follows. I take the product of the first two elements, the first the first elements of the two pairs. And then here I put the augmentation, h1 to the power of augmentation of r2 and h2 to the power of augmentation of r1. And my question was, should I check that this multiplication satisfies distributivity?
So what was the augmentation? So -1 always. Yeah.
Sorry, what about?
What was the augmentation? You subtract the trivial knot or something?
The augmentation is the map in this case from the group ring of Qn into the integers, which sends every element of this group to 1. So every knot or every string link goes to 1, and we just sum the coefficients in the formal linear combination. The augmentation.
So is the coefficient sum.
Yes, just the sum of the coefficients. How many string links we formally took together. So let me try. So R1 maybe okay, R1 plus R1 prime, H1 plus H1 prime times R2 H2. So this is going to be right distributivity, and there is also left distributivity, but I think it is similar. So this should be equal to R1 H1 times R2 H2 plus R1 prime H1 prime times R2 H2. And now we can compute this by this formula. R1, R2, H1 epsilon of R2, H2 epsilon of R1, plus R1 prime R2, H1 epsilon of R2, no, H1 prime epsilon of R2, and then H2 epsilon of R1 prime. And here we have R1 plus R2 times, no, plus R1 prime times R2. And then no, I think this should be written H1 times H1 prime. So H1 times H1 prime raised to the power epsilon of R2, and then times H2 to the power of epsilon of R1 plus R1 prime. Okay, now let me add something. This is easy to add. So R1, R2 plus R1 prime R2, then H1. So this group is abelian. So I can just write that yes, so H1 to the power epsilon of R2, H1 prime to the same power, and then H2 to the power epsilon of R1 plus epsilon of R1 prime. here we have R1, R2 plus R1 prime, R2. And then H1 epsilon to R2, H1 prime epsilon for R2, H2 epsilon for 1 plus epsilon for 1 prime. I think it's the same.
It works.
But I haven't seen such a construction anywhere. So maybe it's a special case of some interesting construction, but I don't know such interesting construction. And now okay, can I continue? Now we consider the homomorphism from ZGN to Rn. So our Gn, as you remember, Gn was the product of Hn and Qn, and we want to decompose it into this product, but of Qn we also remember there's this multiplicities, and here we forget them. So this homomorphism phi is defined very simply. Phi of GH equals GH. So Gn is a product of Hn and Qn. So I can write the pair GH here. And then I just take this pair itself. Well, these are the additive generators of this group. So I can extend it to a group homomorphism by this formula. And I have to check that it's a ring homomorphism. So I can actually write it in more detail. So this is on generators. On the generators. And I can write it on all elements. Phi of M1 Q1 H1 plus so on plus MK QK HK equals M1 Q1 plus so on plus MK QK, and then H1 to M1 and so on HK to MK. A little bit strange. Homomorphism, I count these multiplicities 2 times, here and here.
Что доказывается?
So far I just write this homomorphism on our arbitrary element. So it was given on the generators, and then if you just extend it by additivity, you have to get this, because well, each plus will give you the product here, and I mean each plus here will give you the plus here and the product here, just because the abelian group is written multiplicatively. And then every such factor, well, it has to appear both here and here, because it's how it works. M times QH if you consider it that Qn plus Hn it equals mq h to the power n.
Соответственно, все-таки фи тождественно.
Что фи?
Фи между... Фи не тождественно.
Phi cannot be the identity because these are two different rings. So this equality holds by this definition. You can consider R to be just an integer, which is this integer times the trivial knot, which lives in Qn, or the class of this trivial knot. And then we have to apply this definition, so this integer is multiplied. So if this is m and this is 0, or no, 1, times RH, then we get m times r h to epsilon of m. And this is what I wrote here. So we have such an interesting homomorphism, and we want to check that it is a ring homomorphism. What does it mean? So it means to take product into product. So this can be erased. Or you don't want me to check it? That this is a ring homomorphism, that it is multiplicative.
Сейчас мне просто еще потому что чуть раньше
Ага.
даже находился.
Yes?
Сейчас я попробую сразу понять. Ну, все понятно, да. То есть, вот, ну, фактически можно считать, что эта проверка и написана. Ну, учитывая, что там все коммутативно, ну, надо там аж коммутирует.
No. Окей.
То есть представим, что вот эта вот сумма, она там из двух частей состоит. Тогда, ну, сумма... Сейчас. Для произведения еще можно проверить сейчас.
Maybe I just do, I don't do this sum, but for example I do multiply two elements of this form. M times GH and M prime times G prime H prime. Okay? So phi of this should be equal to for the first one GH times for the second one M prime G prime H prime. So this one is M G H to the M. Yes? Yes. And this one is M prime G prime H to H prime to M prime. This one I think I have to write it first. M prime G prime H prime. So this is M prime GG prime, and then H prime raised to the power M prime. So if I multiply this two, according to this formula, I get M prime, GG prime, H to the M, H to the H prime, no, I have to take into account this augmentation. So H to the M, and then the augmentation of this, epsilon of M prime, and then H.
Epsilon M штрих, это M штрих.
Yes, epsilon of M prime is M prime.
Что значит epsilon M штрих? M штрих это же уже целочисленный коэффициент.
But it's okay because
Имеется в виду штрих равно M штрих читая 1.
by M I mean M times the trivial knot. Okay, maybe you're right. Yes, yes, we already had M prime G prime, so epsilon of this equals M prime. Yes, I should write this. Thank you. H prime to M prime, and then again we take this augmentation, which should be M. And yes, it works.
Можно для сложения все-таки, мы еще не понимаем, вот в сумме двух образов таких вот штук, вот если здесь просто вместо умножения сумму взять, там будут пары, у одной из которых справа h. В общем, вопрос в том при сложении в R, что происходит со вторыми компонентами? Они перемножаются?
Well, let's check.
Это вопрос, то есть в R не определено сложение.
Why? It is defined as a direct sum. Here and here we have the
HN. Это же фактор моноида, кажется.
Well, maybe what is confusing here is that Hn is a abelian group which is written multiplicatively. So R1 H1 plus R2 H2 equals R1 plus R2 H1 H2. So do you want me to check this? No?
Если так, то работает.
Okay. Okay, so we have this ring homomorphism, and we want to compute its kernel. So I think that the kernel of phi contains elements of the following form: Q H prime, H prime H minus Q H prime and minus 1 H and plus 1 H. So we should look at this formula. This formula. So we have a sum of this form. Then we write q minus q here, so we get 0. And after the comma, we write h prime times h prime inverse times h inverse. But it is an abelian group, so we get 1. So this lies in the kernel. And I think it is somehow more or less clear that the kernel is generated by the elements of this type. Because what can happen, how can you send something to 0? You have to have some cancellation here and some cancellation here. And in the domain, the only thing that can happen is that this cancellation is, there is no cancellation because you split them into different pairs. So,
понятно, то есть мы все сейчас, у нас же H и Q первоначально моноиды, значит у них есть, есть ли у них...
Это группа, H и Q это группа. Причем H абелева группа.
Да, я имею в виду, что... Да, это не работает.
I think one, to prove that the kernel is generated by such elements, one has to write some equation, like that phi of this equals 0. So this sum must be equal 0, and this product must be equal 0.
Вот можно рассмотреть, значит, в QN подгруппы, значит, подгруппы, порожденные всеми использованными элементами, в них выбрать базисы, расписать все в базисах. Вот, значит...
Ну, базисов там может не быть, потому что это просто группа, это же не свободная группа.
Сейчас. Ну вот они значит, будут...
Ну, H это еще абелева, H это еще абелева группа, там ладно, а вот QN она не абелева. So, somehow I didn't write up this proof, but I think it seemed somehow obvious to me that the kernel is generated by such elements.
Простите. H абелева, не абелева Q, да? Да. Но ведь у нас ядро, ну, для того, чтобы пройти чем-то ядро, достаточно рассматривать только сложение. Вот, да, я имею в виду те подгруппы уже в ZQN и в HN. То есть ZGN это же тоже ZQN плюс HN. Вот.
Ну, пожалуй,
вот
да.
эти уже обе абелевы, причем, насколько я понимаю, Вот если взять, ну, если, да, возьмем вот эти, значит, элементы, проведем, что это получится конечно порожденная Эбелева группа. У них есть вот не базис, но вот я не помню, как это называется, но в общем, там прямые слагаемые. Вот. И в координатах уже, значит...
Ну да, так, конечно, это можно, но я думаю, что это можно и проще, но сейчас...
А так вообще даже вот сама уже прямая сумма вот этих двух групп, то есть у нас будут просто координаты вида же какой-то аж какой-то, вот и у них все. Сейчас. Каждый из них. Да, каждый из них можно вот как слева сократить, если там сначала, значит, Q1, 1H, 1,1. Вот так, то есть без. Вот если просто. А, нет. Да, если без H', вот тоже соотношение написать, вроде не хватит ли вообще таких без H'? Для чего H'? Да, без H', наверное, сейчас.
I'm not sure if these are enough, because how can you reduce this one to a sum of such ones? If you multiply it, like you can multiply by h prime this two, but then this will be multiplied by h prime also. Well, this was somehow more or less clear to me geometrically, and if you write G, no, if G is QH, no, QH prime, I think, and well, H is just H. 0H. Then this, and then this. No, 1H. Yes. So if you consider the composition of Gn as Qn times Hn, you take the element H here. So it's also an element of G, but if you project this to Qn, it goes to 1. So I should write 1 here. And then this difference is the same as GH minus G minus H plus 1, which is the same as G minus 1 times H minus 1. So, well, I think I have to leave this assertion non-proved because I cannot quickly prove it now. It should be not difficult, but we have to solve some equation. Yes, so we have to write that this equals 0 and this equals 0. It takes some work, I think. Okay, so this part is
Не равно ли q запятая h штрих h такому q запятая h плюс 0 запятая h штрих. Ой, сейчас.
еще раз q.
Да, q запятая h плюс 0 запятая h штрих. То в первом h штрих.
Равно.
А 0 запятая штрих лежит в ядре, насколько я понимаю.
Как это?
В ядре фи лежит. Сейчас. Нет, всегда переходит. Да?
Сюда переходит. Нет, подождите, h1 to 0, yes?
Вот, да, лежит в ядре, потому что m умножить... Сейчас, нет. Может быть, оно равно нулю просто. Вот z, вот если же смотреть как z по n плюс hm, то когда мы умножаем на m, себя. Просто в любом случае это более простая форма, чем соотношение, которое вы написали выше, может быть, вот при помощи него удастся свести.
Нет, все-таки как-то я не уверен, что оно лежит в ядре.
Да не лежит. Это странно. Просто тогда вот заменим соотношение, которое вот там вверху написано из ядра. Вот заменим там вот q запятая штрих h на то, что я предложил. Тогда h штрих будет фигурировать в двух скобках. 0 запятая штрих и q запятая штрих. То есть их, наверное, как-то можно... Да. Значит, тогда просто их заменяем на скобку q запятая 0. И получается, что вот то соотношение выше сводится к такому. Q запятая h. Ну, в общем, вот к тому, которое во второй строке написано, но еще... 。
Какой-то это странный элемент.
Видите? Получается, вот такой вот ядре должен лежать. Нет. Уже у нас операции просто компонентные. Значит, свелось. Я умею сводить ваше соотношение к своему.
Ага. Ага.
Ай, понадобится. Значит, вот. А это получается вот так вот ровно.
Ага.
Значит, это моих хватает, ну и это значит, доказательство того, что мои это все ядро, оно вот, видимо, через байс просто все там расписывает.
То есть вот этот вот просто равен вот этому получается, да? А штрих здесь уходит.
Да.
Okay, thank you. Thank you. Yes, this should be easier to prove that this generates the kernel. But anyway, I think we have to believe it. Yes?
Ну это же должно мгновенно через базис получаться. Вот если мы все расписали вот через Q и H, которые вот в отдельности независимы, там Q между собой независимы и H между собой независимы, и то если какой-то коэффициент, допустим, при Q занулился, значит вот у нас есть фи какой-то комбинации, эту комбинацию мы можем переписать через комбинации Q запятая 1, 1 запятая H, 1 запятая 1. Вот если в образе вот комбинации элементов такого вида что-то занулилось, то там изначально сейчас. Нет, это соотношение зря используем.
Well, yeah, I think we can, indeed, if every element reduces to an element of these forms, then we can just write an equation like m1 times this plus m1 times this plus m2 times this plus m3 times this plus m4 times this goes to 0. And then And then we can just solve this equation.
Если у нас есть элемент ядра, мы хотим при помощи таких комбинаций превратить его в ноль. Значит, ну да, все понятно. Значит, вот у нас есть базис из G, базис из H, и есть, значит, фи от какой-то комбинации G-итых, H-житых. Я не буду писать.
Ну, вот это надо, можно стереть.
По-английски могут быть сделаны линейно независимо. Can
be made linearly independent. Well, I think they can be made linearly independent in this group ring, but here you have to take any elements, right?
Да. Тогда тут еще так, единица, это здесь еще получается нужно. То есть вот фи от 1,1 это
1,1.
Значит, здесь еще единица должна входить. Значит, вот, да, минус сумма. Значит, так вообще.
Ну, подождите, здесь единица и здесь единица, нет? А почему у вас только один раз получилось?
Должно получиться. получаться. А, да, значит, здесь плюс, здесь минусы, их нет просто. Да. Сокращается по-английски.
Cancel.
Так. Вот. Теперь мы знаем, значит, что значит, не так, а вот так, так как из соотношения это by не знаю, by или from.
Смотря что вы хотите.
Из соотношений хочу написать.
By, ну так можно.
Соотношение.
Relation. You mean this? By this?
Я имею в виду, что вот это ядре, наверное, неправильно так говорить. Вот так вот. Значит, вот 0 равно вот этому.
I think here you don't use anything.
Здесь использовал то, что стандарт. Здесь я переводил, как бы выражал через вот такие, через то соотношение. Заменял вот такие на такие, значит образ все еще 0. То есть образ элемента не меняется при прибавлении какого-то количества таких соотношений. Я провел так, чтобы убить эти и превратить их в эти. Вот. Значит, теперь у нас 0 равен вот такому элементу. Значит, из независимости, вот из этого соотношения, из независимости разных вот этих и разных вот этих, получаем, что для каждого и сумма по g равна нулю, для каждого g сумма сумма по и амплитудах равна нулю. Вот это все.
Окей.
Сейчас, и в точности это означает, что это состояние равно нулю. Не означает. Сейчас. Значит, мы хотим доказать, что любой элемент из ядра приводится к сумме вот таких. Если мы хотим доказать, что сумма вот таких, его можно превратить в 0. Значит, если складываемся вот теми, его можно превратить в 0. Значит, я сложил вот с теми и получил элемент такого вида, который с одной стороны переходит в 0, с другой в это. Я хочу... Ну конечно, да. И значит отсюда мы получаем, что вот этот элемент равен нулю. Да. Значит, вот это обозначим через... Как бы обозначить? Ну сильно, допустим, от суммы только маленькая. Не цвет, что заметно будет. Следовательно, цифра равна нулю. Значит, их соотношений хватает.
Yes. looks convincing. Thank you. I think this proves this claim. Okay? Convincing. So we want to, this is a general element of the kernel. But we rewrite it, so we want to prove that the kernel is generated by such differences. But actually such a difference is equal to this difference because of this computation. So this can be decomposed like this, and then we substitute this one here, and we get this. Here it is substituted. This is the same as before, and then this is minus q h over h prime over h prime, which is 1. And so we get just this. So these two are equal. H prime cancels out. So it remains to show that the kernel is generated by such elements. Now we take a general element of the kernel and we apply this relation. Namely, we replace this one by this sum. This plus this minus this. Okay, and now we compute phi of this according to the formula. And we get here the sum of mij from the first term. From the second term we get this product. Yes, and this one is this one gives a sum of mij, but then this one will give a similar sum, so they cancel. Here was the sum, but it cancels because it's I can write plus sum ij mij. But also minus the same sign, sum ij mij.
Еще для Аши такой же будет.
No, this I think this is just one. In
Ой, да, да.
in this group it is just the unit. It should be C. So yes, so this cancel, and we have this and this. And now this equals 0 because here we had this was an element of the kernel. We know that these elements lie in the kernel. So this is still lie in the kernel, but also GI are linearly independent in this group ring, and HI are linearly independent.
Можно выбрать применение логики, которые были изначально.
Yes, I think.
Конечно, порожденные группы, вот у них есть приложение.
Yes, I think if we have, there are different decompositions for finally generated abelian groups. I mean the finite part. But we can choose maybe.
Всегда есть изложение в прямую сумму циклических. Этого достаточно.
Yes, but the uniqueness. Okay, maybe if it is. So you have some decomposition to the direct sum of cyclic groups. On each summand you have 0. No, this you have an element in this decomposition, which on one hand is a sum of some. Okay, so Hn is a direct sum of C I from 1 to some k cyclic groups, and we have here an element of the form some mi xi, which equals 0. Then each mi should be equal to 0. I guess so, yes, because this is direct sum. So we have that mij, yes, we have this. Here in this case it is a sum.
Одна при G, другая при H. То есть первый сумма коэффициент при G и запятая 1, второй сейчас, нет. Вот значит, почему они равны нулю? Потому что вот в этой скобке она вся равна нулю, значит мы берем там вот коэффициент при каждом G равна нулю.
Yes. The coefficient at Gj is this sum. Sum over J. No, the coefficient at Gi is the sum over J of Mij, and it must be equal to 0 because Gi is a basis element, and so by this reason this coefficient, maybe it should be called by a different letter, and this coefficient is 0 and this coefficient is this sum. This I is this sum.
Только тут есть проблема с тем, что вот эти коэффициенты, они все у меня снаружи, но если бы в H были элементы конечного порядка, то могло бы оказаться, что эти m, они на самом деле вот равны порядком. В общем, чтобы с этим не возиться, мне кажется, стоит просто сразу уточнить, что в ZQN очевидно нет элементов конечного порядка, потому что это, это Z на что-то. А в H нет элементов конечного порядка, потому что там...
Why?
Но HN это же...
These are nodes. I think it is unknown whether this group contains elements of finite order. It's an open problem. These are nodes modulus and equivalence. But I think you already get this equation from this part. So the coefficient at Gi will be 0. But here you have the same coefficient. So this becomes 0, and then it means that we expressed an arbitrary element of the kernel in terms of these elements. Because we expressed it in terms of these elements plus something which we proved is 0.
Цепочка такая. Мы при помощи тех привели вот этому виду, а это вот в точности 0 вот здесь написано.
Yes. Okay. Convincing.
И все-таки вот мне прям нужно, чтобы установить, что коэффициент при 1,g равен нулю, мне нужно, вот, что там вот сумма по i равна нулю. Но она ведь может оказаться порядком h.
Нет, подождите, здесь у вас все-таки сумма по g. Значит, this you also need this.
Сумма по i, но коэффициент
Okay, you need both of this, and you have a problem with elements of finite order. So I think it's better to prove not using the basis just for this reason, but probably this can be modified to work without the basis. Well, anyway, maybe it's more or less clear now that this assertion is true.
То есть гипотеза наверняка верна, иначе быть не может. А факт логарифмический, значит доказывается наверняка проще.
No, I suspect that it could well be wrong. Quite well, there can be elements of finite order in this group. They probably just appear at very high levels, so the computations on computers don't see them because they appear quite far. For n equals 20 maybe they appear. And
Такое в топологии возможно?
I think it is quite possible, yes.
А почему?
For example, these elements of finite order then can be related to various symmetry properties of knots, non-invertible knots. If you reverse the orientation of a knot, then it is still not known whether such two knots can be distinguished by finite type invariance. But actually the first example, when such two knots are different at all up to ambient isotopy, appears quite far in the tables. You need many crossings to produce such an example. No, that's a mirror image. And to reverse the orientation of the knot is a more subtle operation. It usually doesn't change the knot type, but for some quite complicated knots it does change the knot type. And also you can consider the combination of reversing the orientation of the knot and the orientation of the three-sphere. So such symmetries are complicated subject, and I think it can absolutely happen that the torsion exists, but it just exists far enough. I don't know. Well,
А все-таки ведь даже если там порядок, все равно вот там ноль получится. То есть мы знаем, что это вот что мы знаем. Мы знаем, что h житое в такой степени равно нулю. Знаем ли мы тогда в Gn, что соответствующая сумма на вот этот элемент равна нулю? То есть, казалось бы, когда мы число снаружи умножаем. Нет, не знаю, нет, там же свободно.
no. Okay, I think this is almost a proof, and almost a proof. So we can continue, I think. Yes. So this is something that I shouldn't erase. So such an element equals this. If we write G as this pair and H as this pair, then this is such difference, which is G minus 1 times H minus 1, and this lives in our delta lambda. So actually these are the additive generators of delta lambda, and also we almost prove that they are the additive generators of this kernel. So we almost proved that this kernel equals delta lambda. Except that, well, yes, it's not exactly like this, because in delta lambda it lives in the group ring of the monoid of string links. And this kernel, so then we have the projection to the group ring of Gn, and then we have this map phi to this ring. So this kernel, the kernel of this phi, is generated, I think, by the image of delta lambda. So it's called, yes, over, well, okay, delta lambda plus Wn over Wn. But maybe it's just better to say that if you look at the kernel of the composition, first P and then phi. Then, well, of course we have the kernel of P, the kernel.
Уважаемые сотрудники, рабочий день окончен. 22:00 будут закрыты двери здания и ворота. Просим покинуть помещение. Пожалуйста, не забывайте выключить свет, закрыть окна и дверь. Всего доброго. Повторяю, рабочий день окончен.
The kernel of P is Wn. So Wn certainly lives in this, and also delta lambda certainly lives in this, because these elements live in the kernel of phi, and delta lambda is generated by their preimages. So I think this is what we get. Yes, I think this is what we get. And this is all that we need from this, or almost all. So now it's almost the end of the proof, and we have just one more lemma, which says that if we take the image of the augmentation ideal, so we have we have our map from that Gn into the ring Rn, and this ring contains that Qn. So here we have the augmentation ideal delta n, and here we have the augmentation ideal delta bar. And I claim that the image of the else power of, maybe I just, no, this should be delta n, because we also have delta here, this delta. This one goes here, because the augmentation commutes with this map. But here I cannot just say that this goes here, no, because there is, in this ring, there is also another part, Hn. So I think it just doesn't work like this. This is the augmentation ideal of this group ring. But I claim that it goes to delta n to the power L for L greater or equal than 2. And here I think we can do some computation. So let's do it for L equals 2. So this delta n squared is generated by products of the type g minus 1 times g prime minus 1, where g and g prime are in Gn. And we have g equals qh, and h equals, and g prime equals q prime h prime. I can write it as a pair, but I can also write it like this, because it's a direct product of groups and it's a product. So this is Q1 times 1H. So then we can write, can I erase this? G minus 1 times G prime minus 1 equals QH minus H times G prime minus 1 plus H minus 1 times G prime minus 1. So this H cancels with this H. And also I can write in the same way that Q minus 1 times G prime minus 1. If I take this H out, then I get this. This equals Q minus 1 times Q prime H prime minus H prime plus Q minus 1 times H prime minus 1. Again, this to cancel. And so we get G minus 1 times G prime minus 1 equals Q minus 1 Q prime minus 1 H prime plus Q minus 1 H prime minus 1 H plus H minus 1 Q prime minus 1 H prime. Actually, this looks a little bit similar to this. But maybe not exactly. So first I get this, then I take this H out, and what remains is this. I simplify this. Here I can take H prime out. So I get Q minus 1 from here times Q prime minus 1 from here. From here. And then H times H prime. So this is this sum. Then this one is this. Q minus 1 times H prime minus 1 times H, because I took it out here. And this summand is this H minus 1 times Q prime minus 1 times H prime times H prime.
Ну, иначе симметрии не будет.
But why? I think I lost something. So this equals h1 h minus 1 q prime h prime minus 1. So maybe I have to write that it equals h minus 1 q prime h prime, but I wrote this. No, I have to do it again. I have to do it again. Yes, okay. Minus h prime plus h minus 1 times h prime minus 1. Okay. So then this gives me this, and this gives me just h minus 1 times h prime minus 1. Okay, so this lives in h k Okay, so this lives in the augmentation ideal which you want, delta n bar. Because this lives in this ideal and it is an ideal, so we can multiply by this. This lives in delta lambda. And this lives in delta lambda.
У нас квадраты должны быть. Вот там квадрат, наверное, стоит.
Где квадрат?
Мы хотим сказать, что квадрат лежит в квадрате.
Yes, so I took the product of two.
Мы хотим сказать, вот там фи.
Sorry, this is squared, yes. This is squared. Thank you. But this is just delta lambda, this is delta lambda, and this is also delta lambda. So, and delta lambda lies in the kernel of this map. We proved that this kernel of phi equals delta lambda plus something. So we get just delta n bar squared. And if we want delta n cubed, then I think we can just use this, because if we have a third factor here, we just multiply everything by this third factor, and because we have ideals, no, here we have to have q prime prime minus 1. We have to do the similar argument. Well, anyway, for L equals 2, it's this computation, yes, and for bigger L, it should be similar. So now we are ready to prove this theorem. Yes, so this map takes as delta n to the power L to delta n bar to the power L. And then this is phi, okay, this is phi, and this is p. And we have the kernel of p. The kernel of p is Wn. And also we know that the kernel of, first we take p and then phi. this is Wn plus delta lambda. So if we add to this kernel this power of the augmentation ideal, we will still get into this augmentation ideal. P and then phi applied to delta, now just this delta to the power L, because this delta to the power L certainly goes to this. It just goes, this delta goes to this delta N. Now, this plus delta lambda lies at least in delta n bar to the power L. Yes, I think it is equality, but we don't need the equality when we need the inclusion. For L greater or equal than 2. Now, this group Qn is nilpotent. And so we can apply the lemma about dimension subgroups to this group. So delta R of Qm equals 1 for some R. Maybe I should call it Q. And then we have that 1 minus Qm intersected with delta bar Q. No, delta bar m to the power Q is 0. The dimension subgroup was the intersection of Qn with this augmentation ideal raised to the power Q plus 1. So this intersection equals 1 is the same as to say that this intersection equals 0. And now we can write 1 minus L intersected with this delta to the power L plus Wn plus delta lambda. So this 1 minus L goes to 1 minus Qn. This goes to this, as we just proved. And so this intersection goes to 0, and that means that it lies in the kernel of this composition, first P and then phi. And this kernel of the composition is Wn plus delta lambda. This is what we had here.
Там написано, что 1 минус L переходит в 1 минус QN.
Потому что this is because L goes to Qn. Yes, thank you. This is a good question. I can replace Qn by Gn here, because this augmentation ideal, the power of the augmentation ideal, it lies in the group ring of Qn, which lies in the group lies in the group ring of Gn. So if I intersect them in this group ring with 1 minus Gn, the intersection is 0. But I think I should intersect them in this ring Rn. Well, it doesn't leave there. Okay. So well, yes. So sorry. So this this lives in the ring Rn, and the ring Rn is a direct sum of ZQn plus Hn. So Gn goes to somewhere in this product. Here we have Gn times Hn. Gn goes to Qn times Hn. Qn goes to this factor and Hn goes to this factor. But this augmentation ideal and its power, it lives here. So if I don't get into this factor, then of course I will have trivial intersection with this power. It only matters if I get into this factor, then the intersection can be non-trivial.
Пока совсем не понял. Вот сначала вот там стрелка — это отображение φp, да? Ну вот снизу.
Okay, so originally we have this. This we know. Now I claim that yes. So I take the sum 1 minus L, which lives here. This link, or yes, this link L, it is a product of some link L prime and some K, where K is totally split. This lives in well, okay, it's class. The class of L modulus n equivalence can be also represented in this way, where this lives in Qn and this lives in Hn. Now L prime goes to this. So okay, so 1 minus L equals 1 minus L prime times K. This and I want a sum probably. I want to represent this as 1 minus L prime plus L prime times 1 minus K. And so this will go into that Qn, and it's so it cannot intersect anything here because this intersection is trivial. I mean, it will go into 1 minus Qn, which leaves in that Qn. Now we have to understand this one. So 1 minus K, I think it just goes to well, we have, yes, it's not clear, you're right. Maybe we have to stop now because it's time. So maybe we leave this as it is, but I try. I hope again that this can be corrected. I hope. So assuming this, we are almost finished. Let me tell you the remaining part, and then this remains a question. So if this intersection is yes, if this lies in the kernel somehow, then this kernel equals this, then we get that we just get this inclusion. Yes, and also we have this V Q times n minus 1 lies in delta Q plus Wn. This was Fourier's geometric theorem. So we combine it and we get the following: 1 minus L intersected with V Q n minus 1 plus delta lambda lies in 1 minus L intersected with delta Q plus Wn plus delta lambda, which lies in Wn plus delta lambda. This inclusion is what we have here, and we assume for now that we know it. And this inclusion is just a consequence of this. I just rewrite it. So then we get this inclusion. So now we can prove this theorem. So we have two links, L and L prime, and we assume that they are not separated by additive type R invariants, where R is Q times n minus 1, and even we can subtract 1. So from this. So they are not separated by locally additive type R invariants. We assume this, and then we need to show that they are not separated by type N invariants. Well, if they are not separated by type R invariants, then their difference, L minus L prime, lies in the subgroup generated by 1 and delta lambda. Because we had this in the beginning, if some invariant, so locally additive means that it vanishes on 1 and on delta lambda. Yes, and here I have to add v r plus 1. Because it's a type R invariant. Okay, but we have the augmentation map from this monoid ring into Z, and it vanishes on this difference L minus L prime, and also it vanishes on this. So this goes to 0, and delta lambda plus VR plus 1 also goes to 0. All this lies in the this is the augmentation ideal, and this also lies in the augmentation ideal. So if we have that this difference lies in something generated by this and 1, then we can remove 1. It is not going to help us, because it goes to 1, and okay. So then let me just erase it, and we have that this difference lies here, and this is exactly this, and again this is a difference of two different links, and here is one link, here is a trivial link minus some link, but again we have two-sided ideals everywhere, so I can just multiply up to Cn equivalence. There is an inverse link to every link, and I can multiply it and get 1, and with some work it can be replaced. So I can put L minus L here. And then, so our given difference of links lives here, and we get that it lives here. But this is a Cn equivalence. So what we obtain is, we obtain that L minus L prime lives in Wn plus delta lambda. And this means that if we take this composition phi p of L, then it equals phi p of L prime, because this was the kernel of this composition.
Простите, я отвлекся.
So we know this from this inclusion. Yes? And this was the kernel of phi p. So L minus L prime lies in the kernel of phi p. And this means that phi p of L equals phi p of L prime. But the last step is phi on G is injective. Because just it was the definition. It was even the identity on G if you represent G as a direct product. So this means that, what does it mean? P of L equals P of L prime. And this means precisely that our links are Cn equivalent. And this is what we wanted. Okay? So there is this problem here.
Сейчас пытаюсь понять, где вообще понадобилось вот РН, дельта с чертой и все вот это.
Well, we needed, we really wanted to understand the kernel. We wanted to understand that lambda modular Wn plus delta lambda. And so this quotient ring. And Rn was this quotient ring exactly. So it was just a description of this quotient ring in closed terms.
Сейчас, разве там любой элемент в образе, если восстановить сумму степеней, должна быть равна сумме коэффициентов?
No. So the kernel of this composition was precisely this idea.
Образ, это же не все, наверное.
It is subjective. Because how it can be not subjective? This is subjective, yes? And this, so if you take any element so Rn is ZQn plus Hn. We can separately represent every element here and every element here. Yes? So ZQn just lives in Gn, in that Gn. So when we take an element from here, we can get any element here. And here we also have a subgroup. We have Gn, and inside of Gn we have Hn. And of course it also goes here by identity. So this is also covered. If these two are covered, then everything is covered. Because it is additive. So Rn was just this quotient ring, but I think we really needed that Qn, that this one is a subring here. Because we wanted to apply this lemma about nilpotent groups to this group Qn. Not to the big group Gn, but to the group Qn. So I think we wanted to find Qn inside of this quotient ring. But now with this problem, yes, I have to think about it, sorry about it. Let's finish, because I think we can have problems. It's too late. Andreas, any questions?
Too much to be asked now. And please understand, I have a bit of geometric intuition. But when you make algebra and write letters that are too small for me to understand, and I have only one chance to trace everything, that I later go through the formula step by step.
Yes, I'm sorry that this proof is algebraic, but I cannot do anything about it. I don't have a geometric proof. And now even this algebraic proof has another problem, which I have to think about. Alright, let's finish that. Thank you for listening. And thank you for good questions. Bye.